All the problems solve the supply and the demand problem. Yeah. Because then the weaker students would be like, okay, I just won't take it. And the stronger students would be like, yeah, I can handle this, it's fine. And then it would reduce the size of the course.
I do know if the students also struggling or distracts most of the students struggling.
I don't think it's anyone else because all the students who would be struggling would just not take it because it's not required for anyone else. I also specifically designed this class to try to beat out.
Welcome to the Triangle Distinguished Lecture Series. It's our pleasure today to have Avrim Blum, who is the Chief Academic Officer at TTI Chicago. Till very recently, he was a professor of computer science at Carnegie Mellon. Avrim is very well known in the theory community, and he has worked on a wide range of topics. When I was a grad student, we knew Avrim mainly through his work in approximation algorithms, but Avrim has done a huge amount of work in theoretical machine learning, and more recently in algorithmic game theory. Avrim has won several awards, an ICML Gold 10-year Best Paper Award, an AI Journal Classic Paper Award. He has been a Sloan Fellow, and has won the Herb Simon Teaching Award, and is a Fellow of the ACM.
Thank you, Kamesh. Thanks for the very nice introduction. I tend to speak a little quietly, so if just raise your hand and wave, or gesticulate if I'm too quiet, and I'll try to speak up. My brain sees that there's this microphone, so it thinks that I'm being amplified. Okay, so let's see. So yeah, so this is joint work with Yishay Mansour at Tel Aviv University, and with my former student, Jamie Morgenstern, who is now on the faculty at Georgia Tech, and with Michael Yang, an undergraduate at CMU. And as Kamesh said, so I was on the faculty at CMU for many years, and just last summer joined TTI Chicago. And so I thought I would start actually by just saying a little bit about what is TTI Chicago, and then before going into the talk, so you know before any YouTube video there are ads. So first of all, so we are a philanthropically endowed computer science graduate institute. So this is us. So what does that mean? We're on the campus of the University of Chicago. So this is University of Chicago, which looks suspiciously like here, actually, in some ways. And there's Chicago. And what does that mean? So we have 11 tenure-track faculty. We also have around 8 to 12, currently 8 3-year faculty, working in the research in the areas of machine learning, algorithms, theory, computer vision, speech, natural language processing, robotics, and computational biology. We have about 30 PhD students. So we're like an academic department of machine learning algorithms and applications inside a mini university of machine learning algorithms and applications. We do not have a football or basketball team. And faculty, tenure-track faculty, and there are research assistant professors. And so come visit. We're actually doing a bunch of workshops. We have a lot of Midwest things: Midwest Theory Day, Midwest Robotics Workshop, Midwest Machine Learning Symposium. But you don't have to be from the Midwest to come. And we're starting up a summer workshop program with workshops on natural language processing, robust machine learning, multi-agent learning, and scheduling and resource allocation. Okay. So now let me go into the talk. So I'm going to talk about learning about agents and mechanisms from opaque transactions. So right. So first let me just start with sort of a very classic problem is given random samples of some function, try to learn a good approximation to that function. Okay. So this is kind of basically all of machine learning, roughly, and lots of work on it. A less classic, but still fairly well studied and a really interesting problem is given random observations of the actions of some agent, see if you can reverse engineer what that agent is trying to optimize. Okay, and this goes under a few headings. In machine learning, it goes into the heading of inverse reinforcement learning. In economics, actually econometrics, and also called learning from revealed preferences, where you watch, say, what somebody buys, and you try from there to figure out what's some sort of preference function over items that sort of explains what they're buying at different prices. What I want to talk about is a setting like this, but where suppose we do not have access to the agent in isolation. And instead, all we get is the result of some multi-agent interaction. So these agents interact, and we see the outcome. Okay, so this is kind of the smoke-filled room in which decisions are made and things are allocated, and we see the outcome. And can we reconstruct from observations of that type, the outcome of this interaction, what the agent's preferences and needs are? That's the kind of problem that I want to talk about. I'm going to talk about a couple of very simple kind of problems in this space. Okay, so for instance, some motivations are observing the outcome of a series of auctions. Like maybe you go to a web page and you see the ads on the page. So those companies won whatever auction there was to show an ad there. So you just get to see the outcome of the auction, who won. You don't get to see the bid, and you reconstruct, possible preferences for the agent. Or from observing which agents end up happy in some allocation process, some allocation mechanism, allocating resources to jobs or whatever, and you from observing what agents end up happy, can you try to reconstruct the needs of the agents and maybe properties of the allocation mechanism itself. So those are some of the kind of questions. So today I'll talk about a few problems of this type. So at the high level, I'm going to talk today about two models. One of them is sort of a classic auction model. This is a repeated auction where each time a single good is going up for auction, and each agent is assumed to have a probability distribution that represents their values. And every day, each agent bids a random value drawn from their own personal distribution. And I'll get back to this later. So they each bid some random number from their own personal distribution. And then, like a classic Meyerson auction setting, but you don't get to observe the bid. You just get to see who wins. So magenta happens to win. Maybe you can participate yourself. So we can bid 50 cents. Maybe we win, and maybe we don't. Maybe magenta wins. And from that, we'd like to recover at least the recoverable part of the distribution. So that's one kind of problem. I'm actually going to talk about that second. I'm going to talk first about a kind of easier problem in some way. It's a combinatorial auction, so it'll be multiple goods for sale, but it'll be easier in that our agents are going to be deterministic. There won't be any probabilities floating around, but their preferences and needs are unknown. This will be more like an allocation mechanism. We've got agents, we've got resources, and some allocation mechanism is allocating these resources to the agents. And from seeing who gets what in different situations, we're going to try to figure out what did the agents want and how is this mechanism working. Okay, that's what we're going to try to learn. Okay, so I want to talk about problems. Those two kind of problems. I'm going to start with this. Okay, so let's consider the following scenario. So let's imagine we've got n buyers or agents. They are. I'll just call them buyers. There'll be m items. So these are the resources. Here are m items. So these, and there'll be a one seller or allocate. Here's our allocate. Okay. So let's say what to think about. These could be jobs, and these could be, say, machines or various sorts of resources. These could be workers at a company. These could be tasks that need to be performed, or maybe these are bidders on putting an ad on a web page. And these are different places that the ad could potentially fit on the page. Every day, so I'm going to talk first about the following setting, and I'm going to make this more precise in a second, but every day a subset of the buyers shows up. You're going to have a fixed set of people, a fixed set of items. And what's different each day is who shows up. Every day a subset of buyers show up, say these three, and we observe that some get something and some don't. So maybe we see these show up. Somehow we see that. We see that maybe this job got this machine, this job got that machine, this one didn't get anything, or this worker got allocated this task, this worker got that task, and this worker didn't get anything. And okay, so that's what happened. And then the next day, a different subset shows up, and we want to try to predict who's going to get what. Right, that's the kind of thing. And we need to assume something, of what's going on. So here's what I want to assume in this first. We're going to look at a few problems. I'm going to assume the following. So imagine what's going on is the following. Imagine that every buyer is what's called unit demand. Look at other scenarios as well. Let's start with every buyer is what's called unit demand. What that means is each one has a subset of items that they like and some preference ordering over it. So if you want to think of as jobs and machines, maybe the yellow job can run on any machine, and maybe it likes them in a left to right order. Maybe the green job can only run on these two machines, and it likes them in some order. Or if these are workers with tasks, yellow can do anything. Green can only do these two. Magenta can only do these two. I like to think of teaching classes. Some people can teach certain things, whatever. Okay. And let's imagine, in addition, the allocator has a priority ordering over buyers. So the way that these are allocated, let's imagine there's a priority, say, over the job. So the allocator has some priority ordering over the job and goes in that order, saying, okay, you're highest priority, take what you want. Okay, you're next, take what you want from what's left, and so on. So maybe that what happened here is these three showed up, and yellow was highest in priority and took this nice red wagon. Green was second and took the Jack in the Box, and then now magenta was last, and oops, doesn't get. Okay, so I'm trying to design a better mechanism. I'm just trying to figure out what the mechanism is that's going on. So maybe that's what's going on. And so, and every day it's going to be a different subset of buyers, and the question is how many mistakes until we catch on to what's going on. Okay, so the particular assumption I'm going to make is the following, that the allocation mechanism is the following very specific thing. The allocator has some ordering over the buyers, and we don't know what that is. Okay, so like platinum level, gold level, silver, bronze, and whatever comes below bronze. Okay, so like that. Or, how much, if these are faculty teaching courses, how much did you pay the department head in advance? I can make those jokes. Right. So, right. So there's some. Okay. So we're assuming that the allocation mechanism has some priority ordering. We don't know what. The buyers have a priority ordering over the items, the ones that they're acceptable to them, and others are just below the bar and they can't do it. So maybe green. This is first. This is second. And the other can't. Okay? So that's the assumption for right now. All right. So this is the problem. What I want to do, let me first talk about a much simpler version of this problem, and then we'll go on. So a much simpler version is what if there's just one item. So let's say there's just one item. The overall mechanism has this order over people, platinum, gold, silver, whatever. And every day, let's imagine show up. Okay, so let's say blue and green show up, right? And we have to guess which is going to get the item. And, blue is going to get it because blue has higher priority, but we didn't know that in advance. We might guess green, we don't know. But turns out, yep, blue wins. Okay, and now the question is, how many mistakes might we make? So every day what's different two people. There's only n choose 2 possible pairs, so clearly we won't make that, that many mistakes. We shouldn't make more than that, but, maybe we should make a lot less than n choose 2 mistakes. And if you think about this for a few minutes, you'll realize this is, like a version of comparison-based sorting, but just of an inverse version, where, normally in comparison-based sorting, you have a bunch of objects, and you want to figure out, their ordering. Algorithm picks the pair, and the world says which one is bigger. Here, the world, the adversary, whatever, the world picks the pair. You have to guess which one is bigger, and then you pay one if you're wrong. Okay? And if you think about it a little bit more, you'll realize that actually you can play this game and make the n log n mistake by simulating the usual sorting lower bound that you might teach in class, okay? The usual, you know, n log n or log of n factorial lower bound. So how do you play this game? Well, there's n factorial orders of these n guys. Throw away the ones that are inconsistent with the previous information. Like maybe yesterday, orange and blue showed up and orange got the item. So throw away all the orderings with blue above board. There's some number left. Now blue and green showed up. Of all the orderings left, some have blue above green, some have green above blue. Whichever has more, go with that one. Every mistake you make, you throw away at least half of the orderings left. So you cut down by at least a factor of 2 at most every mistake, at most log base 2 of n factorial times. You're simulating the usual lower bound. In fact, you can't beat n log n because the lower bound for this problem is merge sort. You can, it actually gives you a lower, but they're really inverses of each other. Now, the algorithm I described is not an efficient algorithm, but actually there are efficient ways of doing it. The old kind of one is turns out you can efficiently sample random linear extensions of partial orders. So basically, there are efficient ways to sample a random ordering conditioned on the partial the partial order information you have. You just sample a few of them. Say, hey, do a lot more have green above blue? Do a lot more have blue above green? Or are they about the same? If they're about the same, you don't really care which one exactly. Or you'll that gives you an efficient one. And there's actually determinants. Okay, so that's the special case of one item. Another special case, which is a special case of buyer, multiple items. So let's say there's only one buyer we care about, okay? And we just want to understand blue. And let's imagine that we have, you know, every day blue walks in, and we get to see what's available and buys his favorite item from what's available. Okay, the reason I want to think of this case is the case I really care about is multiple. Allocation goes through the people in some order that we don't know. If we knew the order, and let's say blue is third in that order, and if we knew the order and we knew what the people above blue were going to buy, by the time we get to blue, we know what's left. Okay, and we would get a problem like this. All right? So if we can solve this, maybe that's a useful subroutine for us. The case, so the special case of the previous problem is what if we already knew the order and we already knew what the people before blue in the order were going to buy, so that by the time it's blue's turn to choose, this is what's left. And now we can't solve this problem. We're kind of dead on the original problem. You know, so maybe given these things, blue gets the red wagon. Maybe the next day, there's no red wagon, but there's a yo-yo, and you know, we try to guess what blue's going to buy. Maybe blue gets the yo-yo. We're trying to figure out blue's preference. Okay, so this is the one-person multiple item case. And well, this is actually, we want to predict the purchase, how many mistakes we make. This is actually the same as the previous problem. Items, people, they're all, you know, this guy has a preference of ordering over items. It's the same thing. And actually, the worst case here is if every day there's just two items. You have to guess which of the two is above the other, and blue's ordering. Okay, because we're just focused on blue. The same problem as before. So the same analysis. This problem, the problem of one person, given a set of items, what's he going to buy? He's got some ordering over them. We can do an m log m mistakes where m was the number of items. It's really the same as the problem we saw before, but the ordering is over items rather than over people. Okay, so the assumption I'm going to make here is the buyer has a subset that the buyer are feasible and then ordering over those. So it could be, and a possible outcome is I will buy nothing. That's illegal. Well, we can look at more general kinds of things where you buy a subset of items. Sure, if you like. Either way, it doesn't. Okay, so I like things that way just because I can draw boxes where it's hard to draw ordering. So good. So general case, n buyers, m items. Here's a natural approach. Let's just run a separate instance of the previous algorithm, one for each buyer, at the same time as we try to learn the ordering over people. It can be a little confusing because we don't know the ordering over people. So, but here's what we can do. We don't know the ordering, so let's put all the people at the top. And we'll just kind of say, oh, let's do it left to right. We'll instantiate a learning algorithm for each one. We'll predict, using our algorithms for each one, an arbitrary linearization of our partial order. So right now it's a partial order. They're all at the top, unordered. We'll just arbitrarily order them left to right and use our algorithms one at a time. So what I mean by that is we go left to right. So magenta, we ask our magenta algorithm, hey, what do you think magenta is going to buy? And it says, I think magenta is going to buy the red wagon. Pull out the red wagon, ask our blue algorithm, what do you think blue is going to buy? And given that there's no red wagon anymore, then I think it's going to be the jack. Great. And we go to yellow, say, all right, yellow algorithm, what do you think yellow is going to buy? Given that there's no jack in the box or a red wagon, I think the yo-yo. Okay, that's how the algorithms operate, and that's how we make. Now we're probably going to make some mistakes there since we just initialized our algorithm and have no information at the beginning. We're going to make some mistakes, and what we're going to do is look at the very first, and only the very first mistake that we make in this ordering. So maybe magenta really did take the red wagon, but blue did not take the jack in the box. That's the first mistake. And maybe yellow didn't take that yo-yo either. Maybe actually yellow the jack in the box. Who knows? So, but with just the first mistake, which is that we thought blue would take the jack in the box and didn't, we feed that into that algorithm and say, you were wrong, didn't buy the jack, bought something else, yo-yo, whatever it was. That's what we're going to do. Why that's a reasonable thing to do, we'll get to later, but that's what we're going to do. And now, our algorithms promised they were only going to make m log m mistakes. What happens if one of them makes too many mistakes? What we do is we take that guy, maybe blue's algorithm has exceeded its bounds. We're going to push blue down one level and restart his algorithm. By push down a level, I mean that now we're going to go with some arbitrary order at the top and then followed by blue. That's the procedure. What you can show is the interesting property that no buyer will ever get pushed below their correct level. You have to prove that, but the claim is that it requires a proof that no buyer will ever get pushed below the true level. Easier thing to see is a person who's supposed to be at the top. But the harder thing is everything else. You can show no one ever gets pushed below their correct level. Since there's n guys and everyone, the total amount of being pushing down is at most 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus n minus. Every time you restart, you make at most m log n mistakes. This gives you at most order n squared m log n. You can also prove a lower bound of n m log m that you need to make at least, it takes m log m to learn one guy, there's n guys, you're going to need to make n m log m mistakes. We don't know in terms of efficient algorithms where's the right. So that's, I haven't proved any of that to you, but I'm just describing the algorithm in the rough. I'll actually give a little bit more of an argument in a second when I do something that's more general. One way to make this problem, I'm going to make it more general in a few steps. One way to make this more general is you can imagine in a lot of like auction settings or economic settings that there are prices. Okay, so maybe every day there's prices on items, in addition maybe to different buyers showing up. And now what buyers choose is, let's imagine how the beginning of a unit demand buyer is every buyer is assumed to have a value on each thing. I buy a toy for my kid, have a value maybe of 25 on the red wagon, and it costs 20. I have a value of 20 maybe on the yo-yo, and it costs 4. Maybe I'll buy the yo-yo, because even though I like the red wagon better, the yo-yo is a great deal. That has a total utility of value minus price of 16, because I liked it at 20 and it only costs 4. We assume that every buyer has a value, a number on each item. There are prices, and selects the item by choosing the thing that maximizes value minus price. That's called the unit demand buyer in the with quasi-linear utility. Another assumption might be that the buyers are additive, that they'll pick all the items with value minus price. I go shopping in the store. I've got a shopping list of things I'm interested in and an amount I'm willing to pay. If for whatever reason, something is way expensive today, I might choose not to buy it if it's more expensive than its value to me, and I just buy all the items whose value is greater, to me, is greater than the price. Okay, that would be a additive. Okay, and then it turns out we can do the same kind of thing. We'll maintain a partial ordering of buyers, where every buyer is assigned to some level. No buyer is farther down than they should be. And on an incorrect prediction, we look at the first mistake in the ordering we make to make progress in that learning algorithm. So what we're doing here is we're running these multiple learning algorithms and somehow feeding mistakes we make into the specific algorithms, trying to make sure that, you know, the mistakes we make are actually real mistakes in some way. Because the problem is these things are all connecting to each other in a function. But the claim is if you do this, it'll be all right. Haven't proven it. Let me now get to a more general principle of what's going on and what we know how to do and what we don't. So here's a more general set, and I'll describe a setting we don't know. The case we do know handle is the following. Imagine every agent is using a decision procedure to decide what to take that belongs to a class of procedures C with the following two properties. Property one is that it's simple enough that we would be able to learn it if that agent was by itself. So if we got to see every day, we got to see the agent walk into the store, what was available, what were the prices, and what he bought. We would be able, in that simpler setting, in the one agent setting, we would be able to pretty soon predict correctly what he's going to buy. What I mean by that is we would make at most, say, M mistakes in predicting what this agent is going to buy. Okay? If you cannot handle the case of one agent, there's no way you're going to handle the case of lots of agents. Special case is n equals 1. Right? So you got to be able to handle the n equals 1 case to handle the general n case. And the n equals 1 case is every day, with some items, with some prices, guy walks in, see what he buys. You have to pick something, you get it right or wrong, you see what he buys, you get your feedback. Next day you make a prediction, you see what he buys, you got it right or wrong, and you want to say, I am. And so he's got to be using a procedure from some class that's simple enough that we can actually learn it if we get that kind of information. Okay, oh, very good. The assumption is the agent here is fixed. And that's a great question of, what happens if the agents are themselves changing over time, and then maybe your mistakes should be a function of how they change. And that's a great question. I don't know how to answer that. But I think it's a great question. I'm tried thinking about, but don't have any good answer. The assumption is the agent is fixed, but just what's different each day is, say, the prices or what's available in the store. But that's the kind of, it's just at these prices he buys this. At those prices he buys that. You just at these new prices, what's he going to buy? Every day you see the price vector, you try to predict the set. So that's property. Property 2 that we're going to use is that the procedure satisfies what's called independence of irrelevant alternatives. I'll say what that means in a second. But under those two assumptions, then, this m, one agent multiplied by at most n squared, where n is the. Now, what is this independence of irrelevant alternatives? Okay. So let me say it kind of math and then in words. So the assumption is that suppose a set of items in the store, I and a price vector p. Imagine the agent would then purchase a subset, j. So we've been looking at a case where it's one item, but it could be that there's several. It could be that, hey, this job needs several resources, to run, and at these prices you'd want to use these resources, and, or at these other prices maybe you'd use, or maybe there's several different sets that would work for you. You could use this or that set, and given what's available, you would choose this set j. Fine. The assumption is that if you, given a set I prime, between j and I. So in other words, if you remove from the store items that the agent was not planning to buy anyway, he still buys j. Okay? So the assumption is that removing items the agent was not planning to buy does not change the agent's behavior. So for example, if the agent is a utility maximizer, you will definitely have this property. If of all then out of all subsets of I prime, j is the subset that maximize utility because there's just fewer subsets to look at. right? It's the smaller set. If J is the argmax out of I, all subsets of I. It's the argmax out of all subsets of I. Okay? So it's a kind of reasonable assumption. But it's not always true. There are non-utility maximizing behaviors that might make sense. So for example, imagine that, you know, you're taking a friend to dinner and you don't want to seem like a cheapskate, but you don't want to spend a lot of money either, so you buy the second cheapest bottle of wine on the menu. Okay? That does not have this property because if you remove the cheapest bottle, which you were not planning to buy, it changes your behavior. You buy what used to be the third. Right? You all been there? So that would be an example of a legal decision-making procedure, but just one that did not satisfy this property. We would not be able to. We don't know how to handle this specific thing. We do not know how to handle it. So the claim is, though, if you have those two properties, then actually this whole thing works. So actually, I'll give you most of the proof. Okay, so here's the proof in 6 easy steps. Okay? Step 1. First of all, algorithm. We just initialize learning algorithms for each agent, put them in a partial order, and then we make predictions by taking our partial order. So we put them in a partial order initially unordered, totally unordered. We make predictions by arbitrarily ordering our unordered sets to convert our partial order into a total order. We go left to right across each whatever. And we just run each algorithm, say, what would your agent buy? And the first one says, I think he's going to buy items 1, 2, and 3. We remove 1, 2, and 3 from the set. From what's left, we ask the second one, what do you think he's going to buy, and so forth. We just do that. That's step 1. That was just the procedure. Step 2. What do we do on a mistake? On a mistake, we update the algorithm for the first mistake in our order. Okay? The first, okay? Now, what happened? We made a mistake. So maybe the very first agent in our ordering we got right, the second one in our ordering we got wrong, that was our first mistake. Now our algorithm thought the agent was shown prime. In this case, what he thought the agent was shown was the whole set minus whatever the first agent was going to buy. Okay, that's the I prime. We thought he was shown I prime. We thought he would buy J prime, but we were wrong. Instead, the agent really selected from a different set I, which we don't know what it is, and purchased some J that we do observe. We observe that he bought J. We know that we predicted he'd buy J prime. We thought he was buying J prime from I prime. We don't actually know what he bought J from. Because maybe he wasn't the second guy in the true ordering. Maybe he was some other thing. We don't really know. So we don't actually know what the agent saw when he chose to buy J, but we know he bought J. All right. What we do know is that this J is a subset of I prime, which is the set of items thought he saw. Imagine that our mistake happened. The first guy we got predicted right. The second guy we predicted wrong. We thought he was going to, but he bought the red wagon. So we thought he was going to get the Jack in the Box, and instead he got the red wagon. Now, okay, good. We thought, I'm just making this up. Okay, so we thought he was going to buy the Jack in the Box. Instead, he bought the red wagon. Now, the red wagon better have been available. If it wasn't available in I prime, which is what we thought he saw, the only reason it wouldn't have been available is someone earlier on our ordering got the red wagon. Well, if this guy got the red wagon, then whoever earlier we thought got the red wagon would have been an earlier mistake. The fact that this is our first mistake means that whatever he bought outside that set, then that's, the only reason it's outside the set is because we thought someone, then we would have made a mistake there. Right. So at least what he bought is a subset of what we thought he saw. The second part of this is that if the agent is at the correct level, and by induction, we should, nobody, okay, we are in this process here showing by induction that no one has ever pushed below their correct level. if he's at the correct level, this won't be true if he's higher, but if he's at the correct level, since by induction no one's ever pushed below their correct level, the set of agents above in our ordering is a superset of the true ones above, because no one's pushed below their correct levels. The people above him in our ordering, people that should be above him, plus maybe other people too. And that means that the set of items we thought he was shown is a subset of the set of items he was really shown. Because in our ordering, there's just more people above him taking away stuff than really there are. Those two together, this is where the IIA comes in. By IIA, since J is a subset of I prime and I prime subset of I, it means that the agent would have purchased J given I prime. So he was shown I, bought J. But he would have bought it anyway had he been shown I prime. It's legitimate to tell our algorithm, you were wrong. You predicted J prime from I prime. Really, he would buy J from I prime. Okay, that's a legal thing to tell it. And that's why we only update our first mistake. Later mistakes, we don't know that just because he bought J from I, it doesn't mean he would have bought it from I prime. He might have, you know. So then we would be telling the algorithm it's wrong when it really wasn't wrong. But here, the first mistake, we know it's a real mistake. We can really charge it to that algorithm. And that's basically put all those together. Okay. Let me use this opportunity to mention a nice open question, which is, it's actually not too hard to learn buyers of the form, I will buy the second cheapest thing in my demand set. Okay, like I like Merlot, but I don't want to seem like a cheapskate, so I'll buy the second cheapest Merlot in isolation. But we don't know how to learn together in this process. Okay. So let me now, switch to the second problem we talked about, and we'll talk about about 10 minutes on this, the Bayesian. I'm going to make the problem easier and harder now. I'm going to make it easier by saying there's just one item. And the auctioneer is very simple, and we know it, which is sell to the highest bidder. There's going to be no strategizing. It's an interesting problem if you add strategizing as well. Let me just pull out strategizing by saying that let's imagine he sells to the highest bidder at the second highest, which is an incentive-compatible mechanism, a Vickrey auction. And then let me say that because of that, let me just assume that everyone bids their actual value. Whether that's a true statement or not, say it, but it doesn't. All right, anyway, so here they are, and they're bidding. Right. Now I'm going to make it harder if the bidders are stochastic. I'm going to assume that every bidder has their own personal probability distribution. And that every day, on day T, at bidder I, every bidder I, on day T, bids a random value from their own distribution. These are independent across the bidders. So every day you press the button, you get a random draw from the purple distribution, sorry, not purple, from the orange distribution, a random, that's this number, a random independent draw from the green distribution, a random draw from the magenta distribution, and a random draw from the purplish distribution. Okay? And they're independent. Then the next day it'll be different, new independent random. Okay? So let's imagine that. So this is sort of a classic auction model. Now maybe just one thing you wonder is why do people bid from a distribution? If they like the red one a certain amount or add on the web page, why don't they just bid the number, deterministic number? Why do they pick a new, fresh, random number from a distribution? Okay, model. One thing is maybe orange is not a person, but orange is a type of person. This is a company in a certain sector. What we can observe about the person. So really an orange is a random orange person from a distribution of orange people. Okay, so something like that. All right, so there's an orange distribution, a green distribution, a magenta distribution, and a purple distribution. You press the button each day, random draws from each. But what do we see? And these are distribution over values or distribution over bids. And what we see, though, is we don't get to see these draws. All we get to see is who wins. We just see the winner, and we can participate ourselves. What we want to do is learn the distribution. Okay, so there's the problem. A bunch of distributions. So, and I want to learn them, let's let's say I want to learn an estimate of their CDF. So if I just had a bunch of orange, if I got to draw 1,000 times the orange distribution, plotted it, I just plot the empirical CDF, it'll be close to the CDF. That's the kind of thing I want to do. Problem is I don't get 1,000 independent draws in the orange distribution. I don't get to observe that. I just get to see these things. Okay. So one thing that makes this hard is even if you see the winning bid, it's not a representative draw from the bidder's distribution. For example, if everybody was bidding from the uniform distribution of 0, 1, the maximum of n random numbers in 0, 1 is not a random number in 0, 1. Okay? It's likely to be on the high end between, let's say, 1 minus 1 over n, 1 minus 2 over n, and 1, and not uniform in this range either. It's going to be, going like that. In fact, the whole problem is in some sense impossible. There's no way you're going to learn what this distribution looks like below 1 minus a couple over n. Below there, it could be uniform. It could be all piled up somewhere. You can't tell because it never wins below there. So, in fact, if we just define, say, p epsilon as a price such that it's very unlikely at most epsilon chance the winning price is below there, we're not going to try to learn the distributions below there. All we can learn is how much probability mass. You say, hey, 80% of your probability mass is below p sub epsilon, and then we'll learn where the other 20% is above there, and here's roughly what it looks like. Okay? Below there, matter, you could mudge it around, you wouldn't notice any difference. The guy never wins. Okay, so we can only hope to learn above a certain level. We can really, it's not hard to see actually. You can only hope to learn the distributions above this level. Below there, it doesn't matter how you move that 80% probability mass. It won't change anything. So there's a really nice tool for this called the Kaplan Meier. And let me just say what it is and how it connects. The Kaplan Meier estimator is something that comes out of medical statistics in the 1950s. And the setting is you're doing a study of the survival rates of patients after some medical procedure. Okay, so you have some new medical procedure, and you have a bunch of patients, and you want to know, what's the survival rate? How many people survive 1 year, 2 years, 3 years, 5 years, 10 years, that thing. The problem is patients keep dropping out of the study. Okay, they move. And so they're not there anymore, so you call them up, a year later to find out they're still around, and, you find maybe they just left town, and they dropped out of the study. And so how do you sort of do that? How do you deal with that? So the assumption underlying Kaplan Meier is that imagine that every patient T lives, they're going to live some amount of time. And let's say there's this distribution D1, which is how long the patient lives after this procedure, some distribution. And let's imagine that they drop out, there's another distribution of how long would it take a random person of the type to get this procedure to, before they leave town. And that's some other yt. And you see whichever happens first. And the assumption is xt and yt are independent. So the event of leaving town is not correlated with how sick you are. Okay, that kind of thing. You have to assume these are independent. Okay, but if they're independent, you see whichever comes first, and then you want to learn D1. And the goal is to recover D1 at least up to the point where most people have left town, in which case you have no population left. And the idea is, you're getting locally good estimates. So at the beginning of 1,000 people, in the first month, 2 people die and 3 leave town. The chance of dying in the first month is 2 out of 1,000, or maybe 2 out of 997. Doesn't matter. They're about the same. And starting from then on, you have 995 people in your study, and just pretend that's times 0 and do the next one. Okay, it's not too hard. You can just chain these things. That's Kaplan. So, when you think about it, this is very much like this auction setting. If you imagine that we get to see the highest, we get to see who wins and what they bid, if you just focus on one person. We just want to learn orange. Think of xt as orange's bid, and think of yt as the max of everybody else's bid. Okay? If orange wins, we see orange's bid. If somebody else wins, we see the max of everybody else's bid. This is just like the previous setting, where we see, instead of seeing whichever happens first, we see whichever is higher. Okay, and this and this are independent draws. They're independent. Orange is independent draw. So this would work to help us. And then the algorithm is basically one that chains down from the top learning the distribution until finally there's a very, very little chance of winning below this price. So that's what you do if you get to see the bid. If you don't get to see the bid, but you can participate yourself, then what you can do is you can try to simulate that algorithm. The main ingredients are you can set a price to see how often, say, orange wins at that price. You can raise your price a little bit and now see how often orange wins and the difference. You can also how often you win at those prices. And from that information, you can estimate how often orange wins, how often orange bids in this particular range, given that nobody else bids above this. That's roughly what Kaplan Meier is on. And then you just have to worry about your errors. Just control your errors to make sure they don't blow up as you change from high prices to low prices. What's a little confusing here is if you discretize things too finely, you end up with lots and lots of things for errors to connect to. But that's okay, actually. You just have to be a little careful. You just view your error as having a multiplicative part and add it all. Okay, you can extend this model. So what if items have a common value component? So for example, if we're selling different sorts of things, this clicker and this laptop might go for different prices. So, what you can imagine, every item has a visible feature vector. So this is this nice red wagon. It's got all these great features, shiny wheels, nice paint job. And the bidders have a common value vector that kind of represents a typical, value on thing W. So let's say this is just kind of how important different pieces are to a typical person. And then you can imagine the value of a bidder I on some item X is the common component, W.X, plus their own kind of personal quadratic noise vector drawn from their own personal distribution. So this is a special case of this is a general case. The previous problem is a special case of this one if you just get rid of this, right? So if there are no there's no common value vector, there's no features, and it's just that's the previous one, but now we can imagine adding this part on. If you knew what W was, you could subtract this off and get the previous problem, but so this new one, in fact, what we'd like to do is learn both W and distribution, and you can do that. You can, basically we'll try to learn that common W, subtract it off, and reduce the previous case, and there's a nice little trick for trying to do that. Bid uniformly at random in a certain range, and you okay. So summarize. So we're considering problems where we want to learn. It's like basically we have a couple examples. Problems we're trying to learn a preference function or a demand set of agents, plus potentially also an allocation process. The challenge is that we don't get to see the agents in isolation. We have to sort of tease out the different components. In some ways, this is like a source separation. We have several sources, these agents, but we don't get to see them in isolation. Instead, they're mixed through this mechanism, which is maybe taking the highest bidder, through them in some ordering. We see some outcome, and now we want to sort of pull that apart and learn the individual ones. We showed we can get efficient algorithms for priority-based allocation mechanisms for fairly general preference functions. And we can get efficient algorithms for single item auctions in the Bayesian setting. I think there's a bunch of nice open problems in this space, some concrete-ish ones. What about other natural allocation mechanisms? So for instance, a priority ordering is one way to, for instance, allocate resources to jobs. You have, priorities over jobs, and they go in that order. But, in auctions, maybe what you do is you might say charge people some amount. One thing you could do is you could have actually the whole bidding part be part of the mechanism itself. Bid on where you are in the ordering and then go through. Or it could be that you go through the items one at a time and have people bid on them. There's a whole zillions of mechanisms. And can you sort of disentangle, can you handle those and disentangle individual preferences in these other kinds of things? So we kind of focused on priority-based ones because they were the cleanest and easiest stuff. Can we handle noise and combinatorial? The first 2/3 of the talk was combinatorial with no noise. Second third of the talk was noise with no combinatorial part. Can you sort of put these together? I have no idea. Analyze other natural classes evaluations. Yeah, okay, good. So that's a good question. Uh, um, yeah, so we haven't thought about it. That's a natural question. Um, one confusing thing, right? So, so like, right, so you could talk about, let's see, the one thing would be, let's just go for something like VCG, which would just, boom, try to maximize social welfare. The problem, right, but I guess what you're saying is let's try to take something. We're going to maybe lose a little bit on welfare, but maybe with the in order to maintain some kind of privacy type. Yeah, um, good question. I don't have an answer. Yeah, no, that's a very natural kind of thing to say. So don't use a priority-based allocation. Yeah, good. So the question is, what if if the mechanism is not strategy proof, then, for instance, what you might learn from here is a distribution over bids, but that doesn't tell you, say, about their value. And that's a nice question, and that's something that kind of goes in the heading of econometrics. People look at, and actually, there's some nice work about the case of, you can just think about that for agents in isolation. What if you just get to observe bids under, say, a first price auction? Then you have to, the problem is if it's not strategy proof, you need to say a little bit about what they think about everybody else. Because it's not strategy proof, you need some, the question is now, how are they strategizing? But it's an interesting question, and I think one could talk about that. One thing what I should say is that one thing you can do with this is the case where it's, say it is, let's say it is strategy proof. We're going to sell the second highest price. But maybe we want a reserve price, make more money, because we'll make more money with the reserve price. It's still strategy proof, we have a reserve price. And maybe that reserve price should depend on the set of people who show up, okay? So you can figure out what that should be if you know the distribution. So one reason you might want to learn the distributions is that once you sort of have them, and then you're not going to get the whole distribution, just the high end, that'll be enough to figure out how to set reserve prices. If you assume that they're not anticipating the future, namely that you assume using this learned information to set these reserve prices later. And yeah, I don't know how to handle that if you kind of imagine that they know these. Yeah, that's right. So that's good point. Right. So as long as the agents are kind of fixed, they're not also kind of adjusting their what's in their head. Right. Then you can learn, so they're behaving according to distribution of bids. You could do that. Now you're only going to get the high end, but that ought to be, and I don't know. I mean, probably a good question to actually go through, because you're only going to get the high end up to at the point at which things you never see wins above there, but that ought to be enough. Two of those to figure out the important part of their true value. Yeah, okay, is it tight? I don't know. I don't know if it's tight or not. It does feel loose because you're really doing one versus the rest, and really you should be able to kind of beat that. But anything we tried to beat that doesn't work. In fact, let me get another open problem, which we don't know how to handle. Imagine that there's just 3 bidders. They show up every day. Imagine you cannot participate yourself. All you see is the winning bidder and how much they pay, which is the second highest price. So imagine, here's the game. There's 3 distributions, D1, D2, D3. Press the button. Random draw from D1, random draw from D2, random draw from D3. I'll tell you which one is biggest, D1. I'll tell you not its value, but the second highest. I won't tell you where it came. Just say the second highest was 30. Something 2 or 3, I don't know. It wasn't 1. From that information, can you So the problem is, so Kaplan Meier is for this like censored observations. You see it unless it's higher. But this is like censored in both directions. Everything just goes out the window. And I don't even know how to handle the case with 3. It's like embarrassingly, we don't know.